Okay, sure. Okay, hi everyone. Today I will talk about my recent work with Roger, Jeff, and my advisor Josh. This is about the Millicharged particle and the dark photon and how they affect each other. Okay, so and the formal title is the Millicharged particle reveals the massless dark photon. So here, this is a summary of the talk. There are several topics I want to cover today. The first is I will give because our main observable is based on the CMB spectral distortion. So I will give a brief introduction of the CMB spectral distortions. And the second thing I will talk about is I will give the brief introduction of the dark photon and the relevant physics process we will rely on to experimentally explore the dark photon, which is the photon to dark photon oscillation. And the third one is I will give a brief introduction of the dark electron, and which is charged under the dark Q1 group. And the fourth one is I will rely on the physics I introduced before to give the constraints on the mini-charged particles. And if I still have the time, I will give the introduction on the inverse problem, which is how the mini-charged particle affects the dark photon's power response. Okay, so now let's begin. The first part is the CMB spectral distortion. So as we have known, the CMB has the spectrum which obeys the black body, which has the black body spectrums, and this is based on the observation which is carried on around 30 years ago, and this is the Kobe virus observations. It's the virus on the far infrared absolute spectroscopy on the Kobe satellite, and from this we can know. Let me give the data set of the Kobe virus, and the x-axis is the frequency of the CMB photon per day, whose unit is the gigahertz, and the y-axis is the intensity of the CMB spectrum, which is quantified by the mega-Jansky per solid angle. And the Kobe virus observation reveals that the data set obeys this shape. It's around the. Do you have any questions? Okay, that is around the 40 beams. And if we do the fit of these around 43 beams, then we'll find CMB. CMB obeys perfectly the black body spectrums, and we can find the temperature of the CMB. CMB is around 2.7 Kelvin. So this is the Kobe virus, the data from the Kobe virus, and the uncertainty of this measurement is around the 10 kJ per solid angle. So you can see the uncertainty is less, or maybe much less than 1%.
Are you talking about the statistical or systematic?
I think this is the statistical uncertainties. Yeah. So this uncertainty, and we find that this is the uncertainty is around less than 1%. The error is less than 1%. So it's very precise measurement. And from this measurement, we find CMB has the black body spectrums. This argument is all based on the standard models. However, if there is some beyond the standard model process, such as the photon becomes the CMB photon becomes the invisible particles after the decoupling of the double Compton scattering, and then we can find is the CMB spectrum gets lower because some CMB photon becomes invisible particles, such as the dark photon we discussed today, or maybe the axion when there is some primordial magnetic field. So the CMB spectrum will get lower. However, as we have known, the CMB spectrum is such precisely measured, so we have so very small error bars. Based on this character, actually we can give strong constraints to such kind of the process.
So something I don't understand about that. I mean, what if, like, if you just remove photons?
Yes. Yeah.
Oh, it's because I see.
Yeah, it's late.
Yeah. It's because you can't you can't just make it a lower temperature. It would change the spectrum, but you're talking about just removing photons, but keeping the same shape.
Yes, exactly.
Okay.
Yes, so just to remove some photons, and also it's after the decoupling of double compensate, right? So you cannot make compensate for photons.
Okay.
What about then the systems then that, of course,
Yeah.
calls the question, what about the systematic error? Because that'll be the thing that's determinant for that.
Yeah, I mean.
I'm just curious to know, I don't know.
Yeah, I mean, here, I think what we consider here is still mostly the statistical error.
But that's not the relevant thing.
Yes.
It's a systematic.
So can you?
I thought we include both. They report like a combination.
Just
like they're both really.
Okay, sure. Yeah. Okay, sure.
Yeah, like the smallest error bars are even a few parts per 10⁻⁵. Statistical and systematic. That's what they claim.
Is the removal of photon independent of the frequency?
I think it is dependent of the frequency because the removing of photon depends on the plasma mass. And the plasma mass, if you only consider the free electron, it's independent of frequency. But there's also some hydrogen contributions, electron bonded in the hydrogen, and then this is dependent on frequency. I will discuss it later. You will see, and it will depend on frequency. I will show it later. Yeah. So this is the physics process we are relying on. And for the future, there's also one proposed experiment which is called the PIXI. And in the future, this is a proposed experiment, and it can give much smaller uncertainty, around the 4 order of magnitude smaller uncertainty, which is around 1 Jansky per solid angle. And also it have like 10 more times of the beams. It have around 10 more times of the range of frequencies frequencies of the detections. So it's much better. And more importantly, it have much smaller error bars, and this can give us much stronger detectabilities. And also, if in the future, if we detect some small deviation of the CMB photon, then we may say, okay, we might find this kind of the photon to dark photon, photon to invisible particle oscillations. So this is the introduction of the CMB spectral distortion.
Regarding that, I mean, presumably there are other secondary things that we know are going to happen.
Yeah.
That are detectable with PIXI, like presumably there's some Y distortion.
Like silk damping, something like this, right? And I mean, I think still, I mean, PIXI is I think our main focus is on the virus. So you say the secondary effect is their effect is around the Jansky. So still, I mean, if we consider this, it's still much smaller. So,
okay.
And also here I think we just do the approximate exploration of the future PIXI projection. So I mean, this we haven't included this, but I think it won't not much change much. Yeah. So this is the basic introduction of the CMB spectral distortion. Okay. So this is the first part.
Can you just briefly say about PIXI? What's the status of it as a proposal? Is it like in good shape? What's the time scale?
No, not good.
They actually changed the name.
Yeah, what's it called now?
Phoenix.
Seems
appropriate.
But I would say here, as I have the technology is all well prepared. So as long as someone have funding, then they can fund it. But so this is just the experiment on table. So this is what I can say. So this is the.
You can use the other boards if you want.
Okay, sure. Yeah, and the second part is about the dark photon. And the physics process we rely on, which is the photon to dark photon oscillation. Dark photon. So what is dark photon? if I want to talk to the media of the popular science, I would say the dark photon is the photon which is dark. But to be more specifically, as we have known from the particle physics, the photon is the particle which is the gauge particle, which is in the U1 EM, standard model U1 groups. So let's say the dark photon is the particle which is the gauge particle which is of the dark U1 groups. And if there is some mixing between these two gauge groups, then we may talk, and these photon and dark photon may communicate with each other. So this is the basic knowledge of the dark photon. And if we want to be more specific, so I will write down the Lagrangian. So I will try to avoid writing too much Lagrangian, but this is what I think is necessary. So the Lagrangian is the first term I write down is the kinetic term of the photon, as we have learned in the ENN. And the second term is the kinetic term of the dark photon. And the third term is the mass term of the dark photon, because we keep agnostic whether the dark photon has the mass or bare mass or not. So we just write down the mass term of the dark photon. And from the effective field theory, we find, okay, we have the dimension 4 operators, this is dimension 2 operators, but we need to write down all the dimension 4 operators, which is not forbidden by the symmetry. But we know we don't have extra symmetry to forbid it. Okay, so we also need to write down. So this is another dimension 4 operator we need to write down if there's no extra symmetries. And given this, we can, as long as the kinetic mixing between the photon and the dark photon is non-zero, and then we can plot this kind of Feynman diagram. This is the bridge to help the photon and the dark photon talk with each other. So given this, maybe the photon can become dark photon, or inversely, maybe vice versa. Maybe if there's too much dark photon in the initial state, then it will come back. But here, what we focus on is these directions, because we assume there's not much dark photon in the early universe. So we focus on these directions. And we know this is the one-to-one process. One-to-one process. So this means that if if we want the energy and the momentum to be conserved at the same time, we should have they should have the same mass. Otherwise, this kind of the transition cannot happen. So the condition for the transition between the photon and the dark photon needed to satisfy these relations. However, we know the photon in the standard model have zero bare mass. It's massless. It's rarely detected by the Coulomb experiment. But we shouldn't forget we are not in a vacuum. We are surrounded by, in early universe, the photon is propagating inside the plasma. So its dispersion relation is changed by several things, like the free electron or the electron bounded inside the nuclear hydrogens. So through this, when photon is propagating through the medium, then it will acquire the effective mass, which we call the plasma mass. And when the plasma mass is the same as the dark photon's bare mass, and then this kind of the transition can happen.
In this case, shouldn't we also have the term proportional to the mass of the regular photon in the Lagrangian?
So that's a very good question. So what I write here is the bare Lagrangian. So we haven't included this term, but if we want to include this term, it's something like this. But this is from the thermal electricity. Yeah. Does this answer your question? Okay. Good. Yeah. This is what I want to write down later. So I just write down previously. Okay, so it's here. So this is the condition for this kind of the oscillation to happen, and this is important in our later discussions. So this is the brief introduction of the dark photon, and as I have known, I have said, we need the effective mass of the photon to be the same as the dark photon. So now I will come to discuss how the effective mass in the of the photon have the time evolution in the early universe.
A very basic question.
Yeah.
So do you assume that for this dark photon, there's some particle that's charged under U1 at a very, very high scale, and there's symmetry breaking that then gives rise to this A prime squared term? Because normally, right, you need that to make the term fully gauge invariant.
Yeah. I mean here, I think what I assume is I keep agnostic where the mass term of dark photon comes from. So
It's some auxiliary field, right?
it's
For the mass.
For the mass.
Yeah, mass is just in this Stukaberg mass, so you know, it's still gauge invariant. Yeah, I mean it can have some source, right? Like
You need a new physical field.
it can come from like Higgs mechanisms. It can also become like some composite particles, like the dark romance or something like this. Maybe. So I think I just keep like agnostic where the mass term comes from. Okay, so
related to previous question.
Yeah.
This makes the fact that the mass is effective mass coming from the plasma. This is where the strong frequency dependence comes.
Yeah, I will discuss it later. I mean, there are two parts. One is frequency dependent, one is not. So, okay, so this is the plasma mass. And
really basic question.
Yeah.
You just assume that every standard model particle is
Sorry?
Oh, sorry.
Yeah.
Do you just also assume that every standard model particle is charged 0 under the dark U1?
I think yes, because you know the standard model. Oh, I mean, what I can say is, you know, naively say it's yes, but if you go through the candy mixing, then the charge you can have some tiny little charge, maybe in the future. Oh, sorry. Oh no, sorry. So the standard model particle has 0 charge. So yeah, just kidding. Yeah, you will see it later. I think because you know the communication between the photon and dark photon is only through this tiny candy mixing. So standard model particle is not charged, even though you do the field rotation. Yeah. So this is so now I will come to, this is just basic introduction of dark photon. So now I will give the introduction how the effective mass, where the effective mass comes from. Okay, so actually the effective mass of the photon have two contributions. And as many of you have asked, so this term is from the free electron. You can see this is not relevant with the frequencies. And but also there's another term comes from the electron which is binded inside the neutral hydrogen. And you can see this term you have the dependence of frequencies. So this one is not. This one is the free electrons. Just go anywhere they want. And this is the electron, which is bonded inside neutral hydrogens. Yeah.
What is Ne?
Oh, Ne is the number density of the free electron, and this is the number density of the neutral hydrogen. Yeah. So so E naught is you can approximately treat E naught is the binding energy of the neutral hydrogen, which this is just comes from the Lorentz models, the ENN. Yeah.
Could you also have contributions from resonances, like from the ground state to the first extent?
Yeah, let me see the ground state effective. Yeah, I mean here I think you know we just naively included all into the binding energies. So yeah, you may say you have some different frequencies. Yeah, I mean then we need to do the sum over this term. But I think here we can well approximate this because you know this is finally we'll see this only finally comes from the refractive index. So I mean it's a good part. I think if you do some rule of all the energy levels, then you'll have around 10% fraction. So this is the classical mechanics. So I think it's well approximated. Yeah. Does this answer your question?
Yeah. Okay. I don't know how important this term is going to be, I guess.
Yeah, I mean this will be important in some ranges. It will be important. So you know, so we have two contributions, and so during the universe evolutions, you know, when the universe expands, the number density, naively speaks, the number density will decrease, so the plasma mass will decrease. But you know, it also have some kind of complicated dependence. So let me just draw how it will change. But also we have the like recombination and reionization. So okay, so let's just choose two benchmark values. The first benchmark value is the frequency is very small, approximately 0. So this term is very small because omega is small, so this term is small. So for the frequency which is nearly 0, so I only need to consider the contribution from the free electron. And in this case, so what I do is, in the high temperature, you have the large plasma mass, so it go down, obey the, the expansion, because this one is number density conserved, so it's just a photon to 1 over z to 3 over 2, and when the recombination happens, it goes down, and going this way, and then the reionization happens, so the electron number, the free electron number, go up, and finally go down. So this is the evolution of the plasma mass which have the nearly 0 frequencies. However, for the case when the omega is large, here let me just choose the benchmark value which is around 5, yeah, let me use another color. But in this case, still in the early times, because they are all free electrons, so they will just go obey this way. But now, yeah, this is the recombination. This is the reionization. Okay, but now when the recombination happens, the number density of the electron goes down. So this contribution just drastically decreased, but this contribution is large. Even though there's some suppression from the hydrogen binding energy, but still we have the much larger number density to make compensate for that. So in this case, the negative term will dominate. So it will just go in like this way. And after that, when the frequency is redshift, so this term becomes smaller compared with this term, and it will go up. So this is the evolution of the high frequency photons. The evolution of plasma mass for high frequency photons. So this is the introduction of how the plasma mass, effective mass, changes during the universe evolution.
So is there a sign issue? Is it omega is equal to infinity?
Yeah.
In the positive term, right? The second term.
Yeah. I mean, here it's like this. So because you only consider this term after the recombination, because before that there's no any neutral hydrogen. But what we can find is during after recombination, the omega is much smaller than E naught. So you may ask whether we go to anomalous region, but no. I mean, we just go omega is in our case always smaller than E naught. Does this answer your question?
I mean, if you write it, if it's the correct sign, it seems to me that if you take omega to be very large,
yeah,
then I have 1 over negative 1.
Yeah.
I just get a plus. You said you drew it as if it became bigger.
No. Yeah, let me show you. So in this terms, omega is approximately omega over E naught, and this one is negligible, so it's approximately. So the sign is okay.
Make point if you take omega really, really small, then
Yeah,
it's
omega is
basically,
small.
basically
I thought
free.
it was I
Or
thought
if
the
you
red
take-
curve was a large omega case. So it's
Big-
not like
Yeah.
Take a
the
large
large
omega, then
omega
it's
is
free, basically. It's like it's treating the electron as free.
Right, exactly.
Yeah, because we need to remember this is after the recombination. So if we say the CMB photon, which is detectable for the virus, and during the recombination, this is much smaller than E naught. So that's punchline. And I have tried. I mean, for the higher upper bound of the CMB photon, I think the omega during the recombination around several K was much smaller than 13.
Maybe it would help us if you showed sort of what range on omega is
Oh,
relevant.
okay, sure. So the omega for the virus is around 60. Yeah, sorry for forgetting this. The lower range is 60 GHz, and the higher range is 600 GHz. And yeah, so this is the range of the detection of the COVID virus. Yeah. So this is now let's come to this. So this is the basic introduction of how the effective mass, plasma effective mass, do the time evolution in the early universe. Yeah.
Very basic question. Can you comment on the apparent divergence when omega is equal to E0?
Yeah, I mean, when omega I think is equal to E0, then you are worried about divergence. But here, actually, in the Lorentz model, we need to introduce the dissipation term, so it will not just diverge, it will regulate it by dissipation term. But here, since it's far away from the resonant peak, so we don't consider this. Yeah, because if you go back to the ENM, you'll find Lorentz model, you have some divergence. Yeah, so this will help you to regulate the infinities. Yeah. Okay, so this is the introduction of the Dachau mass in the universe. Okay, so now, sorry, before this, what I want to comment is, if the dark photon mass is like this, let me give other colors. Okay, so if the dark photon mass is like this is the dark photon sphere mass. So you can see, if I just take a white line as an example, so you can see there is some resonant transition, several polar resonant transitions. And in this point, then the gamma to A prime transition can happen. And this is well known. This is well known in many quantum mechanics. It's called the Landau-Diner transitions. And this means as long as two energy levels cross with each other, then maybe you can the quantum state where you have some leakage to another quantum state. So this is the. So now let me give the discussion of how the. So now let me give discussion what's the transition frequency, the probability. So we have now this is the Landau-Diner transition. And there's I just give the result of the transition probability. Here the transition probability is like this. I will explain the physical meaning later. Yeah, so this is the probability of the Landau-Diner transition. What we can find is if we do the naive dimension analysis, what we can find is this is you have the Iverson square, which is proportional to because you are doing the square of this Feynman diagram. And also it's proportional to MA prime square is over omega. And so what we can find is its transition probability something like this. Okay, it's like this. And the Hubble comes from this term. This is O1, this is from Hubble during the resonance. Yeah. So from this, what we
H res is the Hubble constant at this whatever redshift you're
talking about. It's the resonance. This. Okay. So you need to sum and have this. Sorry, you need to sum different probability, but But here I just say if there's only one resonance, then it's the Hubble. Okay, so this is the transition probability. What we can find is because we have, we always know the Hubble is extremely small in the early universe. Like today it's around 10 to minus 33 eV. But in the early universe it's still very small. Because we have extremely small Hubble, so this term is much larger than 1. So this tells us transition probability is much larger than Iverson square for the resonance transitions. So this is one of the advantage of this kind of experiment compared with the light shining through the wall experiment, because the light shining through the wall experiment is rely on the vacuum transition which is proportional to this square. So this is the goodness of the resonance transition. You can largely enhance the transition probability. And when this transition happens, and some CMB photon happens in the late universe, then some CMB photon will get less, and then we have the apparent spectral distortion. Yeah. Okay, so this is the basic introduction of the Landau-Diner transition. But also there's another thing I want to mention is, if you look at this formulas, you'll find this is proportional to MA prime squared. So what's the meaning of this? The meaning of this is when MA prime squared, MA prime tends to 0. and the probability tends to 0. So the meaning of this is for the massless dark photon. So this comes to the title of today's talk. For the massless dark photon, the transition, photon to dark photon transition, is totally impossible to happen if there's only dark photon in the dark sectors. And I want to say is, since if you look at this formula, since this is this holds for the in our case, which is for dark photon oscillation, but I would say is this is the universal argument based on the field theory. The reason is let me write it down here. So the reason is, let me write it here. Okay, the reason is, sorry for bad management for that one. The reason is, if we do the field redefinition, what we can find is, and if the dark photon is massless, what we can find is, if we do the field redefinition, what we can find is we just kill these operators, and without any other consequence, because the mass of dark photon is 0. So this means we are in for the dark photon have 0 mass, we are in the decoupling limit. So from this argument, we will see this not only holds for the CMB transition, but also holds for arbitrary experiments for the dark photon. So that's the reason why it is extremely hard to go to the massless range of the dark photon to detect the dark photons. Okay, so this is the introduction of the second part, which is the dark photon and the photon to dark photon oscillation.
I want to be sure I assimilated that right. You're saying mixing can't do it, but an intrinsic mass can. Is that what you were just telling us?
What I want to tell you is, if the intrinsic mass is 0, then the mixing is non-physical.
Okay, I believe that. But But you were saying, I thought you were saying the opposite. That I thought I must not have heard you right. I thought you were saying that there was never an effective dark photon mass.
No, what I want to say is, given the assumption that there's only dark photon in the dark sector, and if dark photon mass is 0, then we can never see it. That's what my thing. Okay, so do you have any questions about? Because what we do is
maybe you're saying without the mixing and without an intrinsic mass, you can always diagonalize it.
No. What I want to say is, without mixing, without intrinsic mass, but we have the mixing. Then this mixing is still non-physical. Yeah. That's what I want to say.
That made me sense.
Yeah, because just
you say that you might write it, but you can always diagonalize it.
Yeah, that's what I want to say. Yes, you just.
But if there is coupling to electrons, for example, then you will see it. Maybe it's hard to see, but you will emit only a bright photon, and as it propagates, it will get dark.
You mean with dark electrons, or
because if only A
light,
rather than A prime couples to the current, then you will still emit pure A. It's probably much harder to detect or something.
Well, because you just when you diagonalize it, whatever electron couples
to. But if there is a coupling A,
because what you say is this.
It's a rule that there's never any coupling of.
Exactly. It's only the bright is coupled to this thing, right?
No, but sorry, he never couples.
No. I mean, here.
Visible sector electrons to dark sector photons. That's the definition of.
Yeah, that's the definition. Yeah, it only comes with the Candy mixing. So what do you? Yeah, I understand what you say is if you have this interaction, but it still doesn't have physical effect because the photon just go to photon, A prime go to A prime plus epsilon. So you can see this one still go back to itself. So you still don't introduce the mixing.
You don't introduce the mixing, but the effect is real, right? There will be emission of dark photons. There will be energy non-conservation.
No.
Why not?
I mean, because you don't have the interaction in the Lagrangian, so why do you expect there's the?
If you do your change, A goes to A prime plus epsilon A, put it into the Lagrangian, then you will also change your coupling. So it's either one or the other.
He's changing A prime to A prime plus epsilon A. So if A
and then he will get the term J A prime.
No, I
Which is
I haven't introduced the J prime terms. This is not in the Lagrange.
Anyway, that's
I think he's saying that if you have the mixing term, epsilon FF prime, then you'll have that. I mean, I think I understand the answer, but why don't you answer him?
Yes.
You'll have the, if you include the mixing, but you have the A prime massless, that's the case you're discussing.
A prime massless. A
And
prime
you're finding
massless.
there's still no effect because
Essentially,
that term is somehow illusory.
whatever the electron couples to, you just call that the photon.
exactly. Then of course you have nothing.
And
Right,
then
of
there's
course.
nothing.
Yes.
But if the original coupling was J, then it will be a different theory.
No, original coupling is J. This is that
Then after your replacement, you acquire a new coupling, which is J A prime.
No.
Which is not the
No.
usual.
A to A. So JA to JA. So there's no extra coupling come from. I mean.
Yeah, that's okay. Yeah, just skip it. That's fine.
Yeah. Okay, sure. So because the transition is the field redefinition like this, so you can see you don't introduce. I mean, if you're given this field redefinition, then you don't. The standard model coupling still go back to itself. Okay, so this is the discussion of the second part, which is the photon and the photon. Oh, yeah. So this is the second part. But this kind of argument is given when the dark photon, when there's only the dark photon in the dark sectors. Okay, so if we introduce some dark electron in the dark sector, then the story will change drastically. Now I will give the introduction of this.
Are you going to tell us the bounds later on that Doris sets on this?
Yeah. Then it will based on my third argument, and then finally I will come to discuss the bounds. Yeah. So the third part is about the dark electrons. So what will happen if there is some dark electron in the early universe? The first effect is the dark photon. Yeah.
Can you give us a brief definition of the dark electron?
Yeah, dark electron is the charged particle under the U1 dark group. So which means this is the A prime, this is the so this is the dark electron.
Okay.
Yeah, so this is because before we only introduced the gauge bosons in the U1 dark, but here,
but it does not couple to the usual photon.
I mean it's coupled only through the anti-mixing, and I will discuss it later.
Okay.
Yeah, so in this case, when there is some dark electron in the universe, then the story will drastically change because the first thing is let's just do the analogy of the standard particles. If there is some electron positron in the early universe, then what we have is we'll have, as I have said before, here I just use the free electron as an example. So what we have is this one. This is for the dark photon, for plasma mass in the thermal sectors. And let's do analogy of the dark electrons or dark positron. If there is some chi particle in the early universe, so what we have is like this. Here, E prime is the dark gauge coupling over M chi. Yeah, here I just use the non-relativistic case for the example. If for the relativistic case, you need to replace M chi as something like this, but there's no relevance. So you need to replace this to effectively average momentum. But yeah, here I just talk about the non-relativistic. So you have the effective mass of the dark photon. So given this, the story changes because even though the bare mass, or let's say the intrinsic mass of dark photon is exactly 0, but as long as you have the dark electron in your universe, then you have the non-zero effective mass. So still, let's just review my former discussion with. Let's just do the do the redefinition again. And what we find is, as long as there's some effective mass, then, yeah, maybe I don't know whether it's plus or minus, but as long as we have some effective mass, what we found is the kinetic mixing. We kill the kinetic mixing for sure, because we just want to kill it. However, the mass mixing come back with in the form of the mass mixing. So this enables the transition to happen.
I'm sorry, I missed that. Why did you get an AA prime?
Yeah, because when you let's just do the analogy. So you have the effective mass.
I would have thought the dark electrons gave a mass to the photon, but didn't produce mixing unless there was a coupling, which you said there isn't.
Let me show you. So the mass mix, the effective mass turn is like this before the further definition, and then if you do this.
So you are putting in the mixing.
What I want
even without the mixing, you would have.
Still, I mean, always, kinetic mixing is always, given. So, but what I want to play with is whether the bare mass is 0 or not. Yeah. So in this case, you can see, even though we kill the kinetic mixings, but the mass mixing come back. So it's like a seesaw. You press one side.
You didn't kill the kinetic mixing. You had to have it. It's proportional.
Yeah. But it's not a mixing of the kinetic term. So
he needs to kill it by doing that transformation.
Yeah. You need to kill it by doing this transformation.
It's essential.
Yeah. So I just want to say, I just do the redefinition. Then you kill this, but you get back this. So what I want to say is, it's like a seesaw. It's just like if you press this one side, then you get another side up. So you never can circumvent this consequence as long as there is the dark electron in the early universe. It's not seesaw mechanism, but it's like seesaw.
It's like pushing a carpet down.
Yeah, just like I don't know. Yeah, and in this case, so what we can know is, as long as there's the effective mass of the dark electron, then this process can happen again. So from the kinematics, let's describe it from another point of view. Is from the kinematics, because we know the transition for this transition to happen, we need the effective mass meshes with each other. Then very well we have the effective mass from the dark electron to assist this transition. Okay, so actually this is the most important part of today's talk. This is content of today's talk. Okay, so this is So still, this is the first effect when the dark electron exists in the universe. The second effect is that the second effect is that let me say. So the second effect, let me just erase this. So the second effect is like this. The second effect is, if we have the dark electron and it's mixed with the photon, and then what we have is, what we can find is, as you have asked. So what we have is, actually through the kinetic mixing, the dark electron can interact with the standard model photon. So that's the reason. We call it so this is proportional to E prime epsilon. So from this, what we can know is you can say the dark electron has a effective standard model charge. So that's the reason we call it the Millicharged particle. So that's also compared to our title. So this is the dark electron is a Millicharged particle. So our story finally comes from, so now we can know what's the whole picture of our research is. If there is some dark electron which behaves like the Millicharged particle exists in the universe, then it can help the photon to dark photon transition to happen, or it can assist photon to dark photon transition to happen, because it will contribute to the dark photon's effective mass. So that's the third part. Okay, so these are all basic introduction of the underlying physics. Now we need to give the real constraints on the Millicharged particle parameter space. Okay, so yeah, so now let's go to constraint. Let's go to the fourth part, which is constraining the Millicharged particle. The fourth part is constraining or maybe detecting in the future the Millicharged particles. Sorry. Yeah. Okay. Detecting or constraining Millicharged particles. So because we don't know what's the mass of the Millicharged particle, so we will divide into two cases. The first is Millicharged particle is heavy, then it's the dark matter because it's non-relativistic now. And if the Millicharged particle is very light, then it may be a dark radiation. So we'll discuss these two cases. So the first case is the case for the non-relativistic Millicharged particle, which is maybe the dark matter or some part of the dark matter. For this case, let me just do the plots of the existing constraints. So the x-axis here, the x-axis is the Millicharged mass. The y-axis is the Millicharge, sum of Millicharge. So let me give some benchmark values of the sorry, wait for some time. I need to give some benchmark values to help me to do the plot. Okay, so
units on the y-axis.
Oh, y-axis is just the no unit. This is Millicharge. So I mean, in the natural unit, it's just the one unit. Okay. Yeah. Okay. So the first, let me just before give our constraint, let me just give introduction on some other constraint, existing constraint. The first is it's very well known. It's called the stellar cooling bound because the star can emit Millicharged particle. And during evolution, this kind of emission will make star lose energies, and it will change the star's evolution. So this is called the stellar energy loss bound. And this is some cutoff at around the keV scale because the star's core temperature is around keV. You cannot emit the particle heavier than that, otherwise it's kinematically forbidden. So this is stellar cooling bound. And also, you can have the constraints from the similarly, but it's from the supernova. This is from supernova 1987 day. This constraint. There's a ceiling because in this strong coupling range, the Millicharged is just trapped inside. So this is constraint from the astral particle physics.
So you could put diagonal crosses.
Yeah.
Because that's not allowed.
Okay. Yes. Okay. So this is the constraint from the particle physics. Astral physics, and also we have a constraint from the accelerators. And let me give the constraint like this. So it will exclude the region which is heavier upper than that. So this is the constraint from accelerators. And also, because we're talking about the Millicharged particle coupled with the dark photon, and Millicharged particles annihilation will lead to this channel. In the A prime, you will contribute to delta ineffective. So we also have the delta ineffective bond, which is something like this. This is delta ineffective, including the CMB and BBN. So this is delta ineffective bond. And also, we know there's some direct detection bonds. And this is direct detection. Here I use the dashed line because there's still whether this bond solid or not is rely on whether there's some millicharge particle accumulated near the Earth. But it's possible that there's the paper from Rocky Cove and some other people that the solar supernova shockwave may repulse the charged particle out of our galaxy. So I still use the dashed line. Okay, so this is all the constraints as far as I know. Okay, so let's talk about our constraints.
And this is the effective charge of the Millicharged particle.
Yes, it's stem model charge. Stem model charge.
And units of the electron.
Yes. So now let's get our constraint. Here, let's begin with the. Here, of course, we can give a constraint from the 100% case, but for 100% case, there's already some CMB anisotropy bound, and which is given by I think Cora and some other people. However, so and our bond is comparable, but I think it's not interesting to show here because it's just comparable. It's just but however, for the Millicharged particles fraction, which is around 0.4% or less than 0.4%, then the things is different because in this case, the CMB anisotropy bond rely on the dragging between the Millicharged particle and the baryons. If Millicharged is sub-%, and in the strong coupling region, it has a tight coupling with the baryons, so you can only treat it as the one component fluid. And in this case, you can never have the CMB anisotropy bond. So that's the reason why the CMB anisotropy bond dies in this range. However, our bond, let's see, our bond is only rely on the photon to dark photon oscillation, and this kind of probability is only depend on the dark photons dark plasma mass. So even though the fraction of the Millicharged particle gets smaller, let me use that chi. Fraction of Millicharged gets smaller, but still, the changing of the transition probability is gradual. You never get sudden disappear of the probabilities. So we can give the constraint. For this case, we can give a constraint which is like this. So this is our constraint. Maybe, actually it's like this. So like this. So this is our constraint on the virus satellite. And in the future Pixie experiment,
because I missed something. Does it depend on how does it change with the F dark matter?
Okay, so it changed. The bond gets weaker as the F chi, but this kind of getting weakness is gradual. It's not drastically, but other bonds like.
Why are you specifying 0.4%?
I mean, because this is the fraction when the CMB bond dies. CMB anisotropy bond dies, but I see. Our bond still exists.
Right, but if it were if it were greater than that, your bounds would just get slightly better.
Slightly better, but but just comparable with CMB.
Right.
So
got it.
So because there's something I think if you don't do the particle pheno, you may not know is some bond is strong, but it will have some drastic changing when the fraction decrease. Some bond like us, we just gradually decrease. So our bond will win over many other bonds in the subfraction case. And what we can say, what I want to say is, some people say, okay, so why do you constrain this 7% Millicharged particle? Because the reason is, there's some work use the 7% Millicharged particle to explain the edge anomaly. Because in this case, if you want to explain edge anomaly, you want the baryon to be cooled down, and the Millicharged particle you can let the Millicharged particle plus the Millicharged particle as the heat capacity, and the energy will transfer from the Schlein model baryons to Millicharged particle. There's some argument like Hongwan and the Duff and the Tomer, Flansky, and some other people. So that's still reason, and also the relevant parameter space is in these strong interacting windows. So that's the reason why we still want to constrain the sub % Millicharged. Okay, so this is the constraint from the virus, and in the future Pixie experiment, we know the precision of the uncertainty of the Pixie in the CMB spectrum measurement is around 4 times better than the virus. So here we have around 2 times better in the Millicharged particle parameter space. So we can have this. Sorry?
100 times better.
Yeah, 100 times better. Yes, 100 times better.
I think he wrote 10 to the 4 times better.
I mean, what I want to say is because
It's the square root of the.
yeah, because it's Epsilon squared. So transient probability is Epsilon squared. So when you talk about spatial distortion, it's 4 times 4 order magnitude. But if you talk about the QK, it's 2 order magnitudes.
What happens like a KEV? Why?
Yeah. Okay. So this is a very good question. So for KEV, actually, they will come to maybe the part I may not be able to discuss is for KEV dark photon, because for the lighter and lighter miniature particle, the plasma mass is larger and larger. And however, if it's you want it to be large, but you don't want it to be too large, because in this case, the plasma mass behave like this. This is electron, this is gamma. So if it's too large, then they never cross with each other. So this would maybe, but I think I don't have time. So if I come to the fifth part, I will talk about how to use this kind of character to alleviate star photon constraints. But maybe I don't have time.
What happens when the two curves are tangent? You have like some.
Yeah. If two curves are tangent, then you maybe have some resonance. But in our this is the reason why they have some resonance. Yeah.
Sort of a naive question about regular cosmology. If you, because of this effect, would there be some tiny imprint of this sort of deviation of the photon effective mass on the Pixie?
Yeah, very good questions. Yeah, so you asked about
what would it look like?
Yeah, very good question. You ask what's the specific shape of spectral distortion.
Yeah.
I think in our case, we do find for example, like
no, but even without new physics or exotic dark matter physics, there will be an effect.
Yeah.
Could you sketch it?
Yeah. What I want to say is, for example, for miniature particle cross for dark in this way, you will only couple with only cross with the high frequency part, but not with the low frequency part. So this will help us to have the spectral distortion, which is around something like this, where this low frequency part, this is the critical value for this to go down, and this. But we don't discuss it much because our calculation rely on we are still in the uniform universe approximations. But if you go to the inhomogeneous universe, maybe still this kind of low frequency will still have the contribution. But this is needs a future exploration. But in our case, I think we use the homogeneous universe approximation. So still, I think it's not proper to talk about this in this early stage.
So let's thank Xucheng again.
Yeah, yeah, sorry.
Oh, let's thank him once, the first time.
Okay.
Right.
It will be 2 more minutes. I will talk about one final thing.
Okay.
Yeah, 2 more minutes. Okay, so sorry.
I'm gonna hold you to that.
Oh, sorry. Oh, I have 1 minute. Okay. So this is for the case. The final thing is for this case, we are going to the strong coupling region. So the miniature. Plasma mass is proportional to proportional to the coupling squared, but it's inverse proportional to the mass. So in this range, even though the mass is small, but if we have strong coupling, we can have large plasma mass. But there's another range seen this way. So even though the coupling is highly constrained by the stellar cooling bound, but still, in the light regions, whereas the number density is extremely large, so we can still have the large contributions. So this we can use to constrain the second part. Sorry, just give me 1 minute. Yeah, 1 minute. Sorry. The second part, because I think it's even more exciting, or as exciting as this one. So the second part is for the constraining of the dark radiation, Millicharged dark radiation. Okay, so because we know the dark radiation is constrained by delta ineffective. So let's draw the plot something like this. So here we want to saturate the stellar cooling bound, which is 10 to the minus 14, and x-axis is the y-axis is delta ineffective. So this already exists constraint is from the Planck set y, about 0.3, and the CMBS4 is 0.06. However, our constraint for the miniature particle, if we assume it is thermalized, then the constraint can go way below because you have the large contribution from the dark plasma mass. but it's for the chargeable case. Way below the delta effective case, existing delta effective case. And this is from virus. And for the future Pixie experiment, we can go even lower. And one more exciting thing is there's a benchmark value for this, which is called the freezing line, which means given this kind of the Q chi, there's unavoidable amount of the Millicharged particle will be produced. We can treat it as irreducible background of the Millicharged particle from the plasma until Millicharged particle decay. And this is the freezing line for the ultralight Millicharged particle. And then we can find in our constraints, in the future Pixie, through the future Pixie experiment, we can touch this freezing line. Yeah, so this is all this talk.
And now we're going to thank you again. Thanks.
Thank you.
Yeah, probably better to not do the 2 minutes.
Right. Yeah, I thought it was a very good talk.
9:01. I'll say that.
Shouldn't have tried.
Thank you.
Too much.
Whenever
This
you
is
get
a 10-minute word.
whenever you get to the end of the talk, everybody's mental capacity is already there. So if we try to like actually